After lunch break, my name is Markus Schädel. I'm from Johannes Kepler University Linz, and I'm the session chair of the second collaborative filtering session. We have 4 very interesting papers, 3 research papers and 1 industry paper, covering different topics from multi-interest recommendation, confidence estimation, trending, topic identification, and finally, on the effects of incremental training on neural ranking models. And I'd like to ask the first presenters to come on stage. So the first paper will be on multi-interest learning for candidate matching in recommender systems. And Yuki Shi from Hong Kong University of Science and Technology will present this exciting work. The floor is yours.
Thanks for the introduction. Hi everyone, I'm very happy to share our work, Rethinking Multi-Interest Learning for Candidate Matching in Recommender Systems. This is a joint work with Jingqi, Peiling, Qichen, Yiling, Jaebum, Fang Zhao, and Sun Kim. I will start from some background information and then our method and experiment. I know everyone here are expert in recommender systems. Just some background information related to this work about the candidate matching stage in recommender systems and multi-interest learning. Candidate matching, sometimes also called recalling stage, is to efficiently retrieve a pool of candidate items, like thousands from the huge item pool, like millions of items. This stage lays foundation for the fine ranking. And due to the nature of this stage, for the model we apply, the easier the better, and the faster the better. And this is the target application stage of our method. Then we'll come to some background information for multi-interest learning. So what is multi-interest learning? I give one definition here from my point of view, not the official one. Instead of learning one user embedding, multi-interest recommender systems try to learn multiple user interest embeddings. So why we start to pay attention to this multi-interest recommendation, especially in this stage of candidate matching? It comes with some potential limitations of unified embedding. Actually, first of all, for some algorithms, like especially sequential recommendation algorithms, the user embedding might be majorly affected by the recent most frequent clicks, or other actions, and ignore some other interests. Second, one user embedding actually perhaps entangle the preference on various types of the items, which may not actually be highly related. For examples, our interest on cosmetics may have minor relationship with the preference for electronic devices. Moreover, there are something beyond accuracy. Multi-interest embeddings may help better in controlling diversity. Thus, people are starting to try explicitly learn some multiple embeddings factors for people's diverse interests. Then it comes to a general framework for multi-interest recommender system, which is widely applied in current research work on these topics. Starting from the great paper mine in CIKM 19. It typically involves several parts. For simplicity here, we modularize them in this illustration. The input sequence first goes through a historical item embedding layer and an optional feature enhancement layer. Then a multi-interest extractor will route and aggregate these item representations to several interest representations. Then we'll show more on existing training and serving strategy, especially the training strategy, because our work are actually focusing on this part. The training starts with a selection of embedding from multiple interest embeddings for training in this sample. Typically, it is achieved by using the positive items, which the one the user truly interact with next, to select the most similar user interest embedding for training. Then they typically use a simple softmax. As we mentioned before, when targeting candidate matching stage, there might be millions and even billions of items. If we use full softmax, it will be too computation consuming to calculate the scores of all negative items in the pool. Thus, we sample some negative items for training and use simple softmax. They typically use uniform sampling or log uniform sampling in this process. As for serving, typically all the interest embeddings will retrieve independently some items in the corpus. After briefing the background information, we start our motivations on the work. Actually, most of the existing research effort on multi-interest learning are focusing on either enriching the information on representation enhancement, like leveraging the time information, or using more advanced architectures like graph neural networks. However, we observe some common intriguing phenomena here. The first one is, as shown in figure A, related to sample softmax. We actually observe a large gap when we use sampled softmax with uniform sampling and the full softmax when training these multi-interest learning models. And actually, it's not the case when we learn single user embeddings where the gap is not that large. This phenomenon actually indicate that the current training framework using uniform negative sampling is not that suitable for multi-interest models. The second one is, as shown in figure B, related to routing claps. Recap that we have a routing from items to interests. And however, we observe a kind of sparsity in the routing matrix for many of existing models. We know ideally, we want all the interests to be made up of all relevant items to this interest. But when routing collapse happens, it means each interest representations may only be made up of one most relevant items, which is not intuitively desirable. As these two mentioned phenomena are quite common across various multi-interest methods and different models and informations. So instead of focusing on model design, we try to figure out a more suitable training framework for multi-interest learning. For the first problem, we need to figure out why this uniform sample softmax falls short for multi-interest learning. In fact, we know that actually the learning of multi-interest representations will face an increase of easy negatives compared with learning one unified user representation. Because in the training with each sample, we select and train the representation of only one interest. And a specific interest representation is more susceptible to encountering easy negatives. Consider a user whose historical interactions include food, electronics, and bags. If we and some concept related to bag is activated in this sample, and therefore, if we apply uniform sampling, most negatives are easily distinguished from the representation of the bag concept, and are therefore easy negatives, even though some of them may be informative to the overall representation of the user. To solve it, we leverage an interest-aware hard negative sampling. First, we present an ideal distribution that favors the hard negative items with higher scores related to the current chosen interest concept. Then we present an approximation method to achieve similar result of real sampling from this distribution efficiently. We come through some detail of the design here. Inspired by the design of negative sampling in contrastive learning, we first devised an ideal sampling distribution in our scenarios follows these two principles. The first is the informative negative samples of those the select interest concept is likely to be misclassified to interact with. And the second one is the degree of hardness should be adjustable since the optimal effectiveness of the training may vary on the sample size and data set. So our distribution is subjective to the chosen interest concept and assign the negative items with higher dot product with higher probability. And we have a hyperparameter beta to control the hardness level of the optimal training effectiveness. When beta is equal to 0, it is equivalent to uniform sampling. And when beta is approaching infinity, it means that we only focus on the hardest negative samples. However, directly sampling from this Q beta is actually as computation consuming as the full softmax because we need to calculate score of all the items. So our next question is how to approximate the sampling without explicit sampling from Q beta. Here we resort to Monte Carlo importance sampling techniques to make they have same expectation, but we only need to sample from the uniform sampling and just reweight. In fact, the optimization only reweights the objective for each sample and keeps the sampling procedure a batch-wise uniform sampling. So such a method only leads to negligible computation overhead, and it can be achieved with just a few lines of vector code. To stop the routing collapse problems we mentioned before, here we offer a simple and effective routing regularization strategy on the variance of item to interest routing weights for each interest. So overall, the two design in our proposed REMI framework improve the expressiveness of the multi-interest representation from two aspects: the optimization objective of training and the composition of information. We conduct experiments to answer 5 research questions. Due to limited time, I will simply show 2 here, and if you're interested, please refer to the original paper and welcome for discussion. We carry experiments on 3 data sets, and unfortunately, no online experiment now, and we also have some trials and collaborations in the future. Here in this table, we show that using our framework for training, the simple COMI-REC model will improve a lot over the state-of-the-art multi-interest models. Some of them may use like complex architecture, and some use some enriched information. But we show that just improve the training framework will help a lot in the performance. And this validates the importance of the training framework. And this table demonstrates the improvement of training with our proposed framework over the original framework. We'll conclude with some takeaways and future works. The first thing is on the focus of this work, the training framework, including the design of laws, negative sampling, and regularization, matters a lot for multi-interest recommendation systems, and maybe for general recommender systems. We have learned a lot from the talks yesterday and today on these topics. And the second thing is, we think it's always good to check whether the outcomes or like intermediate outcomes match the original intention of the design. For example, in this multi-interest framework, the initial design, we want the multi-interest models, the multi-interest can really capture the different items, different relevant items. But in fact, if something like routing collapse happens, one interest embedding may only contain the information of just one item. It is do not match our original intention. And the third thing is about multi-interest recommender systems. From our point of view, it's still underexplored. From several experts, I think the first thing is currently they are not always outperforming general interest one, just use one unified user embedding. And the second thing is whether the multi-interest extraction can perform as wanted to capture the diverse user interests remains unknown. It's about explainability. And the third thing is if we can, based on this effectiveness and explainability, we can further leverage multi-interest representations to promote and control diversity in the matching stage. Thanks a lot. This is all for today's talk, and welcome for discussion. Thank you.
Thank you very much. So now it's time for questions. If there are any questions here in the room, please get up, talk to the microphone here. If you want to ask questions on Slido, please do so as well, just scanning the code. You know how this works by now. Actually, Chris has been very active, posting questions on Slido already, asking how to determine the numbers of interests to choose and what is the influence of the beta parameter and how to select this in practice, if you want to.
Okay, thank you. I think the first question is about the number of the interests. This is a good question, and in practice, we empirically find, like, for the data set we experiment on, like 4 to 8 may give the best performance. I think to select the number of interests, the first thing we can do is just to empirically find the best one. But I think the ultimate solution for this is whether we can dynamically set and select this number of interests, because it actually varies not only for different data sets, but also for the different users. Yeah, that's our answer. Thank you. And another question is about beta. Okay, yeah. In our experiments, we also studied the result for different beta. And two summary I can give here is the first thing is the best beta varies for different data sets. But one thing is normally we can get a good result with a moderate beta, like beta equals 1, because beta is exponential, so its range, we can cover the other range just from 0 to like 10. So in our experiments, beta equals 1 can always obtain good performance on these data sets. Thank you.
Thank you. There is also another question. Were hyperparameters of baselines also optimized for?
The hyperparameter of baseline, yes. Like for some parameters, like the number of interests, we have a fixed number for all the method, like 4. And if some method has hyperparameters, we will optimize them according to the setting in our experiment. Thank you.
Thank you. Is there any questions here in the audience as well? No? Oh, there is also just one more popped up. Does your work Does your work plan to combine candidates from various interests? If yes, how? Don't quite get those. Maybe you can have a look at that later on. Can you motivate the selection of metrics? If your goal is to reduce the number of candidates from millions to hundreds, why NDCG at 10 and 50 and not much more?
Yeah, it's a good question. Actually, the selection of our matrix is following some prior work using similar data sets. I think one limitation of our work is exactly we are not able to conduct some very large-scale experiments or some online experiments because we are from schools, from universities. So we also hope that we can have some future collaboration with industry and get this method to experiment on more large-scale data sets and scenarios. Thank you.
Thank you very much. Let's thank the speaker again.